Hello. So for this example, we have a granite wall with a thermal conductivity of 2.79 watts per meter Kelvin. And then we have a left surface temperature, which is 50 degrees Celsius. And then we have 22 degrees Celsius as the air, no? Or yes, the air. And then you have the heat transfer coefficient of 15 watts per square meter Kelvin. So what we want to determine is the heat transfer um, or heat flux to the wall and the wall surface temperature. Now, if you can remember, we know that you have heat going from the hot no, to the cold. And you can already see that based on this diagram, no, if we imagine this, that the heat will go from the 50 degrees Celsius no, to the colder no, temperature. So the conductive heat flux is going from left to right. No? And we don't really know, no, to be honest. What could happen is this could be, for example, maybe less than 22 degrees. Actually, the direction of the convection heat flux could be going from right to left, but we can assume for now that the convective heat flux is going from left to right as well, no? So meaning the temperature of this should be higher, no? So T2, we are assuming that T2 is higher than 22 degrees Celsius. So this is your T2 at this point. So to determine this wall surface temperature on the right-hand side, and then what you want to find the flux over the wall, we can create an equation, no? If there is a simultaneous uh, heat transfer. So the energy or the summation of the energy going in is equal to the summation of the energy going out. So as you can see here, convective heat flux goes into the node. So this will be uh, on the left hand side. So you have Q con, and then on the right hand side you have Q convect. So this is the one leaving, no? So we have the formula already for that. So we have Ka, then you have T1 here, no? So the hot here is T1, so T1 minus the cold is the T2, no? And then all over L, and then equals to HA. So we have HA, and then T1, no? So the hotter here, we are assuming that T2 is hotter than 22 for the air. So this should be T2 minus T infinity. Okay? So as we can see here, we can actually cancel out the A already here. So they have the same surface area. No? So you can imagine this is a 3D surface. No? And probably we can assume that they have the same area. So we can cancel that out. So we already know the K here, the H here is given, the length is also given. We know the temperature the temperature one, we have T infinity as well. We can find T2. So you can already use directly your calculator to solve for this. No? But if we do this analytically, we can simplify this. No? We have to just distribute the K. So we have KT1 minus KT2. Okay. And then the L here could be cross multiplied to the other side. So you have it's equal to HL, right? And then you can multiply this HL, no, or this HL to each of this, right? So this will be HLT2 minus HLT infinity. Okay. So to solve for T2, we're trying to solve for T2, so we have to segregate T2 from this equation. So we can transfer this to the other side, this one to the other side. So transposition will change the sign. No? So this will be positive HL T infinity. And there should be positive K T2. Okay, so dividing this or factoring out the T2, as you can see, and then dividing this by HL plus K, you have T2 is equal to, so transposing, swapping the equations as well, no? So you have KT1 plus HL T infinity all over HL plus K. Okay, so we can use this equation to solve for T2. So T2 here will be, we can just do this one by one. So I will not show the unit analysis anymore since we are consistent with the, or we just want to be consistent with the units available. No? But you have to do this unit analysis anyway to check if the units are correct or indeed correct. So you have K, we have 2.79, okay? And then you have T1, which is 50 degrees. So be careful with this one, right? So we have already discussed before that if this is a difference or temperature difference, it should have, or you don't need to change the units into absolute temperatures. But if this is just T1, oh, it is not a difference, you have to convert this into absolute temperature. So you have 50 plus 273, okay? And then plus H, so H is 15, L is what, no? So L is 20 centimeter. This is also 0.2 meter, no? So you have 0.2 meter. And then you have T infinity. So T infinity is 22. So 22 plus 273. Okay? And then all over HL plus K. So you have H again also 15. And then 2, sorry, 0.2 HL plus K. So 2.79. So solving this using a calculator. Oh, sorry. This is, you have 2.79 times 50 plus 273 plus 15 times 0.2 times 22 plus 273 all over 15 times 0.2 plus 2.79. Okay, so the answer is 308.49. So the unit of this should be in what now? It should be in Kelvin. So you have to also decrease or subtract to 273 to get the value in Celsius. No? So this will be about 35.49 degrees Celsius. Okay. So we are good with the right wall surface temperature. So we want to also find the what is the answer here? Sorry, the heat flux to the wall. So the heat flux to the wall. So actually we're trying to find for small q, right? So since we also have we don't also have the given area, no, right? So this is also consecutively right when we're talking about heat fluxes. So Q con is also the same as Q conv. No? So to find Q con, which is also the same as the heat flux in convection, we can use either of these two. No, you have Ka or Ha, the formula here. But I will just use the conduction. No? So K times T1 minus T2 or all over L. No? So you have 2.79 and then that is 50 minus 35.49. So in this case, you don't need to change the temperatures into absolute temperature since this is temperature difference. And then over L, so L here is 0.2. So the heat flux is equal to, I have an answer here, sorry. So this will be 2.3 watts per square meter. No? So this will be your final answer. Okay, so that's it.